Hello, Honor Chem students. A quick video on how to do stoichiometry with energy. So you were asked to pull out your mole map and add in what we have right here, which is called a mole ratio with energy. And I'm going to show you what that really means, but you're going to find this is very slick and very easy, and it's going to be like one of those. Remember when I told you when we were face to face, there's going to be those times where you're like, yes, I can do stoichiometry with these problems. Well, that's what today is all about. Pretty simple. Okay, so you've added this mole ratio with energy into your mole map that you've pulled out. And so you're coming up with this question that says, is this reaction exothermic? So what we have here is oxygen, and you'll notice that oxygen gas will, if you put some energy in here at 495 kilojoules, it will break up into what we call a free radical oxygen, okay? So this is very unusual to have free radical oxygens. They're not as common as you think. Most of the time oxygen is diatomic, but you can break it up and make a free radical oxygen, and it takes 495 kilojoules of energy to do that. So here is my question. How many kilojoules of energy is needed to produce 12 grams of free radical oxygen? So you would start with your 12 grams of free radical oxygen, and in this case, I'm only using 16 grams for oxygen. It's not diatomic. I'm using the molar mass of pure oxygen, so 16 because it's not diatomic. It's free radical oxygen to 1 mole of free radical oxygen. And then when you look at the balanced equation, do you notice there's a 2 moles here for this energy? So we can do a mole ratio between the 2 moles of free radical oxygen and the energy that is involved. So when you look at that, you end up putting 2 moles of oxygen on the bottom because you want moles of the free radical oxygen to cancel, and you put the 495 kilojoules on top. You do the math, so it's 12 times 1 times 495 divided by 16 times 2 in this case, and you get 196. And then because there's 2 sig figs here, you would report 2 sig figs at 190. Sorry, I think I misspoke. It's 186. And then with 2 sig figs, it becomes 190. So doing a stoichiometry problem is really pretty simple. You can do a mole ratio between the moles that you see in front of as the coefficient in front of the compound or the element with the energy that's embedded in the equation. Oh, by the way, is this reaction exothermic? Hopefully you answered no. This is not an exothermic reaction. This is an endothermic reaction because energy is on, the reactant side. You got it. All right. You might also be given a problem like this where it says if 1 mole of methane is burned, 890 kilojoules of energy is released as heat. Calculate the delta H for this process in which 5.8 grams of methane is burned. Well, the first thing you would have to do is to write the balanced chemical equation. So I know, since I see this word burned, I know this is a combustion reaction. So methane plus oxygen makes CO2 plus water. Then I have to go ahead and balance it. So I put my coefficients here. I actually did the Cho method, 1 carbon, 1 carbon. Then before I had this 2 here, I had 2 oxygen, or I'm sorry, I do hydrogens next. 4 hydrogens, so I have to put a 2 here to get 4 hydrogens. And then I have 2 oxygens plus another 2, so there I've got 4 oxygens. Perfect, it's balanced. But do you also notice that I added 890 kilojoules on the product side? That is because it said that 890 kilojoules of energy is released. So that means the energy has to be embedded on the product side. So I went ahead and did that. So now it's just a simple stoichiometry problem. You're going to start with your grams of CH4, and it looks like you have to figure out how much energy because they want a delta H. And remember, delta H is energy. So I start out with my 5.8 grams of methane, and I converted it into moles. So I used the molar mass to do that. And now here I'm using the mole ratio with energy. So when I look at that, 1 mole of CH4 is related to 890 kilojoules. So the reason why I have 1 mole here is because there's 1 mole of methane, and the energy that's associated with 1 mole of methane is 890 kilojoules. So when I do this math, I come up with 330. So that's stoichiometry with energy. And as always, if you have any questions, don't hesitate to email me. Have a great day. Talk to you guys later.